Another type of nuclear decay is the positron decay. It is when nucleus gives away a positron. Positron is a particle very similar to electron, but it has a positive charge. So here we have a nucleus of sodium-22. It is an unstable nucleus, so to gain stability, it releases positron. Mass of positron is 0 and charge +1. So what should be the remaining nucleus? It should be something with 10 protons. So the 10 protons tells us that this element, newly formed nucleus, is nucleus of neon. And mass is not going to change because positron, just like electron, has such a small mass that it's negligible. So loss of positron or electron does not change mass of the nucleus. Let's run a quick check of whether our reaction is written correctly. The atomic numbers over here should add up to the atomic number on the left, and they do. And since our positron, just like electron, has very small mass, so small that we consider it to be negligible, the mass is not supposed to change, and the mass, as we can see, remain the same. And now let's look into the matter of nucleus producing positrons. Up until now, we've been talking about nucleus being made out of protons and neutrons, and no positrons had been mentioned before. So where are they coming from? In beta decay, electron was the product of the decay of a neutron. We mentioned already then that subatomic particles such as neutrons and protons, they have the decay of their own. Neutron decay produces proton and electron. The proton decay produces a neutron and a positron. Let's see how proton decays works. Here's my proton. Proton has atomic number of 1 and mass number of 1 because it weighs 1 atomic mass unit. A neutron produced in the result of it. The mass number of neutron is also 1 because both proton and neutron weighs 1 atomic mass unit, and neutron has no charge, so we are putting 0 over here. Also, a positron produced. A positron has almost no mass, so we're putting 0 for the mass number, and it has a positive charge, so positive 1 goes over here. This positron is released in the nuclear decay, in the positron decay, and we see that there is a decrease in the number of protons in the nucleus because one of those protons that used to be in the nucleus of sodium decayed, forming a neutron. Neutron remains in the nucleus, it's sitting there tight, but this positron is released. Along with the release of positron, some energy is released as well, and the newly formed nucleus of neon is more stable than sodium-22. Here is the way to represent a positron, but you also can represent it with the Greek letter beta. Once again, for positron, you will have to report mass as 0 and charge as positive 1. Now, pause this video and try to figure out what kind of particles, what kind of decays represent these reactions. These reactions have empty spaces. To write in them, you should write those particles that were released along the formation of those nuclei on the right from the arrow. Okay, here's my take on it. Over here, I see that the atomic number went up and nothing happened to the mass. Mass didn't change. It means that I'm talking about beta particle. I'm talking about a charge, an electron. So what should be here? There should be a number that when we add it to 91 should create 90. So it's got to be -1. So over here, it is a beta particle. It is an electron that was released here. Over here, I see the decrease in the atomic number, and I see the decrease in the mass. So I think it's clearly an alpha particle that was released over here, which I will represent as the symbol of helium. And those numbers, 84 plus 2, make up 86, and 206 plus 4 will be exactly 210. Okay, the last one, magnesium decays, and we see decrease in the number of protons, and we see no change in mass. So apparently it was a positron that was released over here. It was something with almost no mass, and the number that should be here, when we adapt it to 11, it should make up 12, so it should be positive 1 over here. So the first reaction represents beta decay. The second is alpha decay. And the last one is a positron decay. Now, as a practice, let's run decay of these elements. But immediately there is a question, what kind of decay should it be? Should it be alpha, beta, positron decay? This question can be easily answered if we refer to the table N. Table N in your reference tables has set of nuclides, radioactive nuclides, and information about the mode of their decay. Here is francium, here is potassium 37 and potassium 42. We can see that francium 220 undergoes alpha decay. So alpha particle is formed, and let's figure out what is the remaining nucleus. It's supposed to have 85 protons, so it is astatine element, and the mass of that particular isotope of astatine would be 216, 4 atomic mass units less than francium 220. Potassium 37 undergoes positron decay. So a positron is formed, and we expect decrease in the number of protons, and the same mass remains. Element number 18 is the argon. Another isotope of potassium, potassium 42, undergoes beta decay. It will be producing an electron with the negative charge, and we expect the number of protons to go up. So calcium 42 is formed. Quick check for our correctness of our reactions. Those numbers at the bottom should add up to the number at the bottom on the left, and numbers at the top should add up to the number at the top. If it's true for all of our reactions, it means that all of them are written correctly. Now, let's talk about energy that is released in the process of nuclear decay. Unstable nucleus can release excessive energy by producing gamma rays, high energy packages of electromagnetic radiation. Gamma ray production accompanies all types of nuclear decay, so it doesn't really matter whether we're talking about alpha, beta, or positron decay. Gamma rays produced alongside with them. This is why we call unstable nucleuses radioactive nucleus, because they produce the rays of energy, the gamma rays. Gamma rays is a type of electromagnetic radiation. And it's not like magnetic radiation is something new to us. We actually constantly exposed to the visible light, which is not dangerous to us at all. We cannot see, but we are quite readily using the radio waves and microwaves and infrared waves as well. They are not dangerous to us because they carry, these types of electromagnetic radiation carries relatively small amount of energy. But beyond the visible spectrum over here, we'll see ultraviolet, X-ray, and eventually gamma rays. The more to the right we are moving on this scale over here, the higher is the frequency of electromagnetic radiation. The wavelengths of this electromagnetic radiation is getting shorter from left to right. And as it happens, the frequency increases and the amount of energy that this electromagnetic radiation carries getting bigger and bigger. And gamma rays are dangerous because it is electromagnetic radiation that carries huge photons of energy and can be very, very dangerous because of that. Here is how we represent gamma rays with the Greek letter gamma, like this, and it is energy, so it has no mass. Energy is massless, and unlike any of the previous particles that we've discussed, it has no charge whatsoever. So 0 goes for the charge and 0 goes for the mass. It appears almost harmless, having no charge and no mass, but on the contrary, this is the dangerous part of nuclear decay. This is the one that is causing so much harm. It's not the alpha or beta or positron that really attacking the body and causing all the mutations in the organism. It is those huge amounts, huge photons of energy that gamma radiation carries. And while we are not writing them at the end of each reaction, they are there. It is assumed that any kind of nuclear decay, alpha, beta, positron, they're all accompanied by the production of gamma rays. Let's see at how penetrating are different things that are produced in the nuclear decay. Here is a comparison between alpha, beta, and gamma rays. Alpha particles can be stopped easily by a thin sheet of paper. That's good enough to stop alpha particle. Beta particles would be able to go through the sheet of paper, but they can be easily stopped by the aluminum foil or your skin. If you are showered by beta particles, the skin is good enough to protect you from any of them going through you. However, when it comes to gamma rays, they go through pretty much anything, paper, aluminum, majority of living tissues. They go through the living organisms and almost nothing stops them. As they travel through, gamma rays carry a huge amount of energy with them, and that is why they are so harmful. The last thing to discuss today is how alpha and beta and gamma rays behave in the magnetic field. If we will send a ray of beta, alpha particles and gamma rays through the magnetic field between the electric plates, one charged with a positive charge and another charged with a negative charge, we will see that the alpha particles will be attracted to the negatively charged plate because the alpha particle has a positive charge. Alpha particle made out of 2 protons and 2 neutrons. It has a positive 2 charge. It will be attracted to the negatively charged plate. Our beta particle, being electrons and negatively charged electrons, the beta particles will be attracted to the positively charged plate. But gamma rays will ignore all the plates. Gamma rays does not have charge and will proceed in a straight line.